The IOM head, seen on the right, consists of two main components. These are the main body, which attaches via flexible tubing to the sampling pump, and a removable cassette, shown here being disassembled so that a pre-weighed filter may be installed. The cassette is then inserted into the body when sampling is to take place. Note the spring clip used for transporting the loaded cassettes before and after sampling. The UK AEA head is an alternative to the IOM head. It does not have cassettes that can be preloaded and must be loaded immediately before sampling. The filters therefore have to be transported separately. The SimHead cyclone, like the IOM head, has removable cassettes that can be preloaded and transported to and from the sampling site. When tightening up this head, as with all the heads shown on this tape, care must be exercised not to cause the filter paper to twist or tear when applying the final torque. The Higgins cyclone, like the UK AEA head, has to be individually loaded prior to sampling. This requires that pre-weighed filters must be transported separately. Again, care must be taken when tightening up the head, and you must ensure that the two O-rings are correctly positioned, one below the grid and the second on top of the filter. In handling this cyclone, it was assumed to be clean. On disassembly, please remember that in all cyclones, the grit pot will contain dust. Do not invert the cyclone until the filter is safely removed. Sampling pumps can maintain very stable flow rates, even against varying pressure drops, but they must be calibrated so that the flow rate is accurately known. Here is a calibration rig. It consists of a soap bubble meter, an adjustable gauge that indicates flow rate, and an adjustable gauge that indicates the pressure drop within the system. The soap bubble meter is our primary standard against which other flow gauges are checked. Due to imprecision in reading the soap bubble meter, longer times, that is, larger volumes, are usually used than is shown here. To adjust the flow rate of the sampling pumps, an appropriate tool is inserted into the screw that controls the flow and is turned until the flow gauge shows the desired flow rate. An alternative secondary standard to the flow gauge, as shown before, is the variable area meter or rotameter. These are light and robust, and once calibrated, rarely change. Here we see an instrumental system that includes all the types of atomization commonly used: electrothermal or furnace atomization, flame atomization, and atomic vapor or hydride generation. We will discuss them all in more detail later. These are some of the hollow cathode lamps, which are used to provide the atomic emission spectrum necessary for this technique. Note the very slow pulsing frequency used by this instrument manufacturer. In this case, we are using flame atomization, which is the most common method hygienists will come across. The variables are flame temperature, mainly selected by changing the fuel and oxidant gases, and whether the flame is oxidizing or reducing. These flames are aeracetylene flames. They are stoichiometric, reducing, fuel-rich, lean, fuel deficient, and again stoichiometric. In spectrophotometric techniques, it is essential to tune the monochromator to the correct wavelength to optimize the instrument. In atomic absorption, this is easy since we have a stable emission spectra to work with. coming from the hollow cathode lamps. Atomic absorption spectrophotometry obeys Beer's law in that the concentration of the analyte and its absorption is linearly related. Here we see a computer-generated calibration curve that shows this relationship, as well as some deviation at higher concentrations, which is typical of atomic absorption techniques. Now you will need a pen and paper to take down a few details for the exercise that is in your notes. We will zero the display by aspirating deionized water, which is assumed to be copper-free. The display now reads 0.001 absorbance unit. The first of our copper standards is 0.5 micrograms per milliliter. This gives 0.211 absorbance units. The second standard is 1 microgram per milliliter. This gives 0.407 absorbance units. The third standard is 1.5 micrograms per milliliter. This gives 0.567 absorbance units. The fourth standard is 2 micrograms per milliliter. This gives 0.729 absorbance units. Now we have our sample, which is referred to in your notes. This gives 0.483 absorbance units. So far we have seen the use of the air acetylene flame, but here we see the use of the other common flame type, the nitrous oxide acetylene flame. This is a much hotter flame, but is more difficult to work with. The use of other once common flames, such as the air propane and the nitrogen-hydrogen entrained air flames, have been largely discontinued in favour of other methods. Although this is an example of atomic absorption, it can be clearly seen that atomic emission is also taking place in this flame. After flame atomization, the next most common technique is electrothermal atomization or furnace techniques. Here we see the main power controller for the graphite furnace. And here is the workhead, which contains the furnace and its associated automatic sample injector. This is an example of a nebulization deposition system where the sample is sprayed as an aerosol into a hot furnace as opposed to the more common direct liquid injection technique. After the sample is inserted into the graphite tube, the heating cycle continues to dry the sample. Ash it at a moderately high temperature. Here we are using 1000 degrees Celsius. And then atomize at a much higher temperature to volatilize the element. Here, 2200 degrees Celsius. The last major method in atomic absorption is atomic vapor generation. This relies on reducing the analytical element in the sample to a volatile species, such as the elemental state for mercury, or to some volatile hydride for the metalloids, arsenic, selenium, germanium, etc., which is subsequently decomposed to the elemental or atomic vapor by thermal decomposition in a heated quartz tube. After the formation of the volatile species, it is either pumped into a closed-loop system where a steady-state reading is obtained, or it is purged from the reaction vessel and is seen by the system as a transient or peak, as here. The equipment necessary to generate atomic vapour is reasonably simple, in this case no more than an automated peristaltic pump, magnetic stirrer and gas control system. But the main difficulty lies in getting the reduction chemistry correct for the element of interest in the given sample. Ultraviolet visible spectroscopy had been the mainstay of analytical chemistry and hence occupational hygiene until the advent of more modern instrumental techniques in recent years. There are still many analytes where the cheapest, quickest method is a colorimetric wet chemistry method. Here the samples are inserted into the optical path of the instrument and a readout, in this case a spectrum in the UV region, is quickly obtained. Another spectroscopic technique that is useful, if less commonly used, is infrared spectrophotometry. Liquids, gases and solids may be examined by this technique, and because, like UV, this method also obeys Beer's law, accurate quantification is possible. Because of its usefulness in the identification and quantification of vapours, infrared is more commonly met by hygienists in the field in portable instrumentation such as the Myron series from Foxborough. As stated earlier, solids can be analysed by infrared methods. Here we will see the use of the direct on-filter method for analysing for crystalline silica on a respirable air sample. With most samples, no pretreatment is necessary because of a lack of interfering species. Where these species exist, however, such as in coal dust, substantial pretreatment is required. Whenever organic vapours in air are the problem, the normal instrumental method will be gas chromatography. This system is complete with a thermal tube desorber, normal injectors, two types of detectors, and the combined integrator chart recorder. The heart of a GC is the oven, where the separation of the analytes of interest is performed within the chromatography column. Here we can see the column connected to the injector on the left and the detector on the right. The original gas chromatography columns were packed metal tubes as shown on the right. Some analysts preferred rigid glass columns because they were more inert and gave better separations in some instances. These have both been made obsolete by the introduction of fused silica capillary columns, which possess separation powers unheard of in the packed column era. This is the gas control system for the detectors and for the column and injectors. Predominantly, samples to be introduced will be liquids and will therefore be injected by syringe. Note that the injection must be a smooth, continuous operation for optimal results. To show the separation ability of capillary columns, here is a real-time separation of a sample of butane gas from a cigarette lighter after direct injection as shown previously. Organic vapour sampling tubes can be dissolved by two methods. One, by extraction with a suitable solvent, usually carbon disulfide, or two, by thermal desorption. Here is a tube being loaded for desorption. It is very important to avoid touching the tube as it is removed from the oven to avoid burns. After being placed into the heated chamber, an exact amount of gas is drawn through the tube to elute the collected solvent vapours. These vapours are then held in the gas syringe until injected into the GC. The gas with the eluted vapours is then dispensed via a gas switching valve into the GC carrier gas line prior to the injector. High-performance liquid chromatography is similar to gas chromatography in that a fluid is pressurized to drive it through a separation column and onto a detector, in this case a UV diode array detector with associated computer data station. Here is the HPLC pump, which delivers solvent at pressures up to 30 megapascals and flow rates of 1 to 10 millilitres per minute. Below it is the gradient controller, which allows different solvents to be mixed to alter the polarity and solvation properties of the running solvent during the chromatogram. The injector allows small microliter volumes of sample to be injected into the running solvent. The analyte is swept onto the separation column where various components are retained to a greater or lesser degree before being delivered to a UV diode array spectrophotometer. A more common detector would be a single wavelength UV detector. The data collected by the detector is here displayed by the data station so that data manipulation may take place, such as integration, baseline corrections, etc.